In section 3.2, we're learning about critical values and relative extrema of functions. So when we say relative extrema, remember this could be a relative maximum value or a relative minimum value. Sometimes instead of calling these relative max or mins, we call them local. So we want to associate relative or local extrema as meaning the same thing. All right, so if we look at this graph of a function f shown below, we're asked to determine the location of any relative or local extrema of f. So if I'm looking for a relative min or a max, that's going to be the highest or lowest, depending if it's a max or a min, point in its local vicinity. So all the other points around that point will be either lower than it if it's a maximum or higher than it if it's a minimum. So if we take a look at our graph, I'm going to zoom in. Tracing this function, like if I start at the left, I get to this spot about here, where it looks like right around here, I'm going to have a local maximum value, because after that point, this function starts decreasing. So I'm going to just go ahead and call this point A. So if I think of this as an ordered pair, this would be A, comma, f of A. So if I consider this, A is the location of a relative maximum value. If I asked you what the actual relative maximum value is, the value is the function value. So the maximum is f of A. If we continue kind of tracing our function, we said this function is decreasing, and then where x equals 0, this function starts increasing again. So at x equals 0, we have a relative or local minimum value. Because again, if I zoom in, that particular point on our graph is lower than all the other points in its vicinity. So again, this the actual minimum value would be the function value at 0. All right, finally, if we look at this third piece of this function f, as I trace it, I notice that this piece is strictly increasing. So there's not any point on this curve that is going to be lower than all of the other points around it because of this arrow. Like this arrow suggests that this curve keeps going down. Maybe we have an asymptote there. And this arrow on the right suggests that this curve keeps slowly increasing the way it is. It almost looks like it's a logarithmic curve there. I'm not sure. So all that to say, there's no relative or local minimum or maximum on that curve because there's no point that's higher than or lower than the points around it locally. So another thing we need to notice is that the relative extrema we found both occurred where something important is happening with our derivative. So at our relative max, I notice that my function is smooth here. When I zoom in on it, again, I can see that it's locally linear. So that means the derivative exists there. And I also know that if I were to draw a tangent line at this max, this would be a horizontal tangent line. So this location is where our derivative is equal to 0. So our derivative equals 0 there. If I look at what's happening at x equals 0, I notice that my function is not locally linear there. I had part of what kind of looked like a quadratic or some type of curve, and then I have this corner where this function changes to something that looks maybe more, I don't know, maybe that's an exponential curve. We don't have enough information to tell just from the picture, but at that spot right there, this function is not locally linear. That's another way of saying that is it's not smooth at that particular value, and sometimes we call that a corner. So remember, when this happens on the graph, this means that our derivative does not exist there. So when we're working with a function, anywhere that its derivative is either 0 or undefined is going to be a really important value. In fact, it's so important that we call them critical values. So a critical value of a function or a critical number is a value of x, it's an input, and it is a critical value of f if that is where our derivative is 0 or is undefined. And if we looked at the entire ordered pair on the function, so like a f of a, for example, we would call that a critical point. So this is a critical point of our function, a f of a. So is 0 f of 0. So a critical value exists if f of a exists. So f is a critical value at x equals a if f of a exists and f prime of a is either 0 or undefined. So in this first example, we are asked to find the critical values of f of x. So the first thing we need to do is find the derivative. So using the quotient rule, I have x minus 2 times the derivative of my numerator minus my numerator multiplied with the derivative of our denominator over x minus 2 squared. So remember, we're going to be looking for where f prime is 0 or undefined, and f prime is a rational expression. And so one way or another, we probably want to simplify our numerator, and we may want to pull out a GCF. So notice that in our first term, we have a factor of x minus 2, and then a factor of 2 and a factor of x. In my second term, I have two factors of x times x is x squared, and a factor of 1, but we always have a factor of 1. So we do have a GCF. If I find my GCF of my numerator, it's just x. So if I pulled out an x, what I'm left with, this is just a personal preference. I like to offset my GCF with brackets. You can use parentheses though. I'm left with x minus 2. I still have that times 2 that I need to distribute, and then minus x. So the reason I'm factoring our numerator is at some point we need to do this. It'll make working with this derivative much more helpful in just a moment. So if we go ahead and distribute our multiplication of 2 over that subtraction, we have x times, again, I like to use brackets to offset my GCF, 2x minus 4 minus x. All right, and then finally, 2x minus 4 minus x is just x minus 4. So now that I've kind of cleaned up my numerator, I'm going to switch back to parentheses. The whole brackets thing is just a preference for me. It just makes it easier for me to see that my GCF is on the outside. We could treat those brackets like we would parentheses. Okay, so this is our derivative f prime. And we said we're looking for critical values of f. So the first thing I might consider is, where does f prime equal 0? Well, remember, if I'm working with a rational expression, aka a fraction, I only need my numerator to be 0. Because if my numerator and denominator are 0 at the same time, I know that that's actually something I have to investigate further, right? If I have 0 over 0, that's one of my indeterminate forms when I think about limits. So that would not technically be the number 0. Okay, so f prime is equal to 0 when our numerator is equal to 0. So one of the reasons I factored it is that now we can use the zero product property. If we had not factored it already, we would need to do so now. So we get that at x equals 0 and at x equals 4, those are the two locations where my derivative is equal to 0. Now I also want to consider where my derivative is undefined. So I know f prime is undefined. I'm going to write D and E for does not exist when my denominator is 0. So if x minus 2 squared is 0, well, that's where x minus 2 is 0, and that's at x equals 2. So our task again was to find the critical values of f. We need to remember that for these to be critical values, either f prime of a is 0 or undefined, but also f of a must exist. So if I look carefully at these three numbers, I know f of 0 exists. When I plug 0 into my function, I get 0 over negative 2. That's a number. That's negative, or that's 0, excuse me. That's not negative 2. That's 0. If I plug in 4 to my function, I get 16 over positive 2. Well, that's a value. But if I plug in 2 to my function, I get 4 over 0. So f of 2 does not exist. So really what that means is that x equals 2 is not a critical value, but it's still going to be a really important value. So it's good that we found it. Like, we need it, but it's not a critical value. So our critical values of f are x equals 0 and x equals 4. All right, I'm going to come back to this example in just a moment. Our second example is built off of this. So one of the reasons that we need to think about critical values is they tell us possible locations of relative extrema. So relative extrema also help us think about when a function is increasing or decreasing, and vice versa. Knowing intervals of increase or decrease could help us think about relative maxes and mins. So everything in this next box is so critical. So f is increasing at a particular value x equals a if f prime of a is greater than 0. So remember, f prime, our derivative, that tells us the rate at which f is changing. So for f to be increasing, f has to be changing at a positive rate. All right, so f is increasing when f prime is greater than 0, is positive. F is decreasing at x equals a, so any particular input, when our derivative is negative. So that makes sense. For something to decrease, the rate at which it's changing must be a negative rate. F has a relative or local maximum at a particular value x equals a if f prime changes from positive to negative at x equals a. So if I think about that, when f prime is positive, I know f is increasing. When f prime is negative, I know f is decreasing. And if I imagine changing from increasing to decreasing, that's going to look like a relative maximum. So similarly, f has a relative or local minimum when f prime changes from negative to positive. So again, where f prime was negative, f was decreasing. Where f prime is positive, f is increasing. And if I kind of imagine changing from decreasing to increasing, I'm going to have a relative or local minimum. All right, so for the second example, we're asked to find the location and value of any relative extrema of f, and then determine the intervals on which f is increasing or decreasing. So the first thing we would need to do is we would need to find our critical values. And more generally, we need to find any place that f prime is equal to 0 or f prime does not exist, like f prime is undefined. Now, we already did that in this last example. So we said our critical values, again, were when x is equal to 0 and to 4. But even though it's not technically a critical value, we also need to consider what's happening at x equals 2. Because our function is not defined there, we could tell that our function has an asymptote there, because when we plugged in 2 to f, we got 4 over 0. So something interesting is happening there. All right, so that's really our first step in this process, is we're going to find anywhere our derivative is 0 or does not exist. The second thing that we're going to do, and I'm going to insist that we do the second thing, is we're going to then make a number line. All right, so when we make a number line, we're going to put all of these values on it, so our critical values, and really anywhere our derivative doesn't exist, even if on a technicality it's not a critical value. And when I put these three numbers on my number line, and this number line is really, it's representing like the x-axis, right? And we have broken the x-axis up into 4 intervals. So the first interval is from negative infinity up to 0, then 0 to 2, then 2 to 4, then 4 to positive infinity. So our goal here is that if we're finding the location of and then the value of any relative extrema, what we're looking for is we're looking for where our derivative is changing signs. So what we're going to do on our number line is we're going to test the signs of our derivative. And when I write that, I usually write it up top, and I'm going to label this f prime so that these signs make sense. Now, if you ever do something like this on a free response question, technically the readers don't actually look at your number line, but I promise you this is a really helpful tool because some of these questions will get really complicated. All right, so if I plug in any test point, I'm thinking of any number between negative infinity and 0. I don't want to choose 0. It needs to be less than 0. I'm going to think about my derivative. And all I really need is the sign of my derivative. So going back to the derivative that we got in our first example, we said this is x times x minus 4 over x minus 2 squared. Now, again, factored form here is going to be really helpful because I could just think about the signs of the factors. So for example, in the denominator, as long as I don't plug in a 2, I know plugging in x equals 2 will make my denominator 0. Any other time, my denominator is going to be positive because whether x minus 2 is a positive or negative number, I am squaring that value. So with the exception of at x equals 2, my denominator is always positive. So I could really just think about the signs of my numerator. If I plug in a number that is less than 0, so a negative number, x is going to be negative because it's a negative number. X minus 4 is also going to be negative. So when I multiply two negative numbers and divide by a positive, my quotient is positive. So on the interval from negative infinity up till where x equals 0, my derivative f prime is always positive. And if I think about what that means for my function f, that means my function f is increasing on that interval. All right, now let's check our next test point between 0 and 2. So I'm going to erase these signs. If you want, you can actually plug in a value here. Let's try it that way. Let's plug in the number 1. You could plug in any number between 0 and 2, but 1 seems like the easiest. So if I find f prime of 1, that is 1 times 1 minus 4 over 1 minus 2 in parentheses squared. So I get 1 times negative 3 over, let's see, negative 1 squared, which is positive 1. So I get a negative 3 here. So my derivative between 0 and 2 is always going to be negative. It's not always going to be negative 3. But I know that my derivative won't have another sign change there between 0 and 2 because f prime isn't 0 anywhere between 0 and 2. All right, so I know if my derivative is negative there, my function f is decreasing. All right, so then we need to consider what's happening between 2 and 4. So again, we could plug in the number 3. You could plug in the number 2.1 if you wish. We could also really think about the signs. So I think it's fine to show your work for where you're evaluating f prime of 3, but I bet we could figure this one out just thinking about the signs of our derivative again. So let's say that I consider the number 3. Well, if I plug that in for x is positive. 3 minus 4 is negative. And we said our denominator is always going to be positive because we are squaring our denominator. So in our numerator, we're multiplying a positive number and a negative number to get a negative number and dividing that by a positive number. So f prime is still negative on this interval. So f is still decreasing on this interval. All right, finally, our last interval from 4 to infinity. Again, we could think of any number that's greater than 4. Or we could just think about plugging in numbers greater than 4. If I'm actually evaluating my derivative, I'll probably think about the number 5. So if I plug in, say, a 5 for x, well, 5 is positive. 5 minus 4 is positive. And again, our denominator is always positive. So our derivative is a positive number times a positive number divided by a positive number, which makes our derivative positive. So f is increasing from 4 to infinity. All right, so after we've made our number line, when I go back to answer this question, it's actually a couple questions. Find the location and value of any relative extrema of f. Then determine the intervals on which f is increasing or decreasing. So we've got our locations, we don't have our values yet. So anytime I am answering this as part of a free response question, I really need to justify my reasoning here. So we could say that f has a relative maximum value at x equals 0. So again, as I'm looking at this number line, the reason I draw these arrows here is this helps me visualize that at 0, I have a max. Now, at x equals 2, I have neither a max nor a min, but at x equals 4, I can see I have a minimum because my function is changing from decreasing to increasing. So to justify that we have a maximum, I just need to go back to what is written in this box. F has a local maximum value at x equals a if f prime changes from positive to negative at x equals a. So f has a relative maximum at x equals 0 because f prime changes from positive to negative. So notice I said f prime has a relative max at 0, not that the relative max of f prime is 0. Because remember, x equals 0 is the location, but we were also asked to find the value. So we need to know f of 0, and we kind of actually did this up in this top example. We plugged in 0 to f, and we got 0 over negative 2. So f of 0 is 0. So our relative max is 0 and is the output. All right, we also have a relative minimum value. So f has a relative minimum, and you can abbreviate like I am, at x equals 4. And again, I can see this in my number line. And going back to the justification, well, we justify a relative or local minimum at a particular value because our derivative is changing from negative to positive at that value. So f has a relative minimum at x equals 4 because f prime changes, not goes, but changes from negative to positive. And again, that's happening at x equals 4. So again, our relative minimum value is not 4. That's just where it's located. We need to actually find f of 4. And again, back up here in part A, I started to do that. If we plug in a 4 to x squared minus x over, divided by x over minus 2, I'm going to get 16 over 2, which is 8. So since f of 4 equals 8, the relative minimum value is 8. Okay, so we could say f of 4 equals 8 is the relative minimum value. All right, so as I reread this example, we've answered this first question. And it was a lot of work. We had to find the derivative, we had to find our critical values, we had to find anything that makes our derivative undefined. We made a number line, we thought about intervals, we answered our question, and we justified it. We also have one more question to answer, but we've done a lot of this work already. Determine the intervals on which f is increasing or decreasing. So I would follow all these same steps. I would find my derivative, find my critical values, or where f prime is undefined. I would make a number line. I would do exactly what I just did. We are now just answering a different question. So if we're thinking of these as steps, step 3 is answer the question. Just make sure you answer it fully. So answer the question and justify, I should say, because we need to justify our reasoning. So we're asked to determine the intervals on which f is increasing or decreasing. Well, again, we know that f is increasing anytime f prime is greater than 0. And remember, our number line is representing intervals. So we could say that f is increasing on the interval, well, our first interval, where f prime is positive, is from negative infinity to 0. And then the second interval where f prime is increasing is from 4 to infinity. So I'm going to use the union symbol to join my two intervals here. So f prime is increasing on negative infinity to 0 and 4 to infinity. And that's because f prime is greater than 0. Or you could say f prime is positive, either or. But we must justify how we know f is increasing. And then furthermore, f is decreasing on the intervals from 0 to 2 and from 2 to 4. And remember, f of 2 doesn't exist, so f isn't really decreasing at 2. But if you were to write this as one interval from 0 to 4, that would probably be okay, because f prime is never positive at 2 or anything like that. So f is decreasing on 0 to 2 and 2 to 4. And again, that's because f prime is negative, or f prime is less than 0.